So Miriam, don't let me distract you. You're doing good. Okay, so it looks like you guys are picturing it pretty well. You're talking about how when you look at a graph, it grows and then grows faster, or it starts decreasing really fast and then slows down. It looks like you guys tried to describe it pretty well. Lesson 2, week 6. Oh, okay. Remind me about that actually, Unique. And at the end, we'll look at lesson 2 from week 6. How about that? How about that? Because I'm not sure. Maybe this is lesson 2. This could be your lesson 2 from week 6 because I believe this is from week 6. But anyway, and then you guys had some good examples. The U.S. debt is definitely growing exponentially. And then, oh, Katie, here comes Katie. Let me put her in, although she missed our warm-up. So yes, the U.S. debt, I like that, Trevor. And then you say Unique, you said, oh yeah, starting a business, that's right. And when you start a business, it could potentially grow because you start off and you're not making very much money. And then, hi Katie. And then as you start to do well, grow pretty fast, you can grow exponentially. That's just true. And then population, that's a really good one actually. Bree said that one because if you think about having 2 kids and then each of those 2 kids have 2 kids and then each of those kids have 2, your population definitely can grow exponentially. So what we're going to do is build some exponential functions, and we're going to build them with transformations so that you can understand what they look like visually. But basically what you guys are seeing is that it's a function that's not a linear function, right? And it's not actually a quadratic function because a quadratic function curves like it's going to be exponential, but then it goes up at kind of a constant ratio, whereas, or I shouldn't really say that, it goes up at the same rate versus exponential, which goes up faster and faster and faster and faster. So it has an increasing rate each time. So it's a little bit different. All right, you guys, so there aren't 2 weeks remaining, just in case you were excited. There's only 1 week remaining after this week. So, all right, you guys, so what we're going to do here is a graph of exponential growth, and these are 3 different functions. See, and actually what I'm going to do is show you the actual graph that I got from Desmos. And now you guys can see this graph. You can see the tail end of it as well as how it grows. And you can see that it comes kind of flattish, and then it gets steeper, and then steeper really, really, really fast. And if I were to keep going up, you can see how it keeps getting steeper and steeper. So that's basically what your graph is looking like. So we're going to look at some key points here. Go back. We're going to start with our parent functions. So there's a lot of different parent functions, you guys. There's y equals 2 to the x, 3 to the x, 4x. There's also 5 to the x, 6 to the x, 1/2 to the x. The point is there's a lot of different parent functions. So anything that's a number raised to the x power is considered a parent function without transformations. So what we're going to do is kind of examine these parent functions and how they work. We're going to look at the base, which is called the common ratio, or if we were applying it to something like population, or if a business is dying, potentially, we could call it growth or decay rate. We're going to look at the asymptote. There is one. And then we're going to determine what this 0.01 represents. Because notice that all 3 of these parent functions go through this same 0.01. All right. Before I continue then, you guys, any questions, any comments, anything you want to go over at all that I said? Anything confusing? You guys are all good? Okay. All right, so when we start off, we're going to always key points. All right, so we're going to start off with -1. Oh, there's green. Oh, well. 0 and 1. And those are always the 3 key points we use. Because you notice what happens if I use like negative, and let me go back. What happens if I use -5? Well, or -6? There's not going to be really a lot of good graphing from those points. Same thing as if I come out here and say I used 4. Oh my gosh, look, I can't even see 4 on this graph. I'd have to go up for a long, look, it's taking forever to get to 4. Still haven't got to 4. Oh, okay, finally now the red one has gotten to 4 about. But The point is, you don't really want to pick points that are far to the right or far to the left. Plus, -1, 0, and 1 are kind of special. They relate to our function in a special way. So let's look at what happens when we put in -1, first of all. Well, if you guys remember your properties of exponents, which you just finished doing, if we take 2 to a -1 power, remember that anytime you take something to a negative power, it just means take the reciprocal. So that means take it as 1 over 2, and then it would be to the +1, which is still just 1/2. Okay, so I'm going to write these down. So this is 1/2. And then notice what happens when we take 2 to the 0 power. Well, anything, oh, Katie, no, 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 no. So anything to the 0 power is going to always be 1. So 2 to the 0 power is 1. 5 to the 0 power is 1. 100 to the 0 power is going to be 1. Okay, and then now I'm going to take 2 to the 1 power. Well, anything to the first power is itself. So notice this key relationship here with 2. At negative, it's going to be 1 over the base. At 0, it's always going to be 1. Notice how these all go through 0, 1. And at 1, it's always going to be the base, 2. So if I look at it from the perspective of 3 to the x, then it's pretty easy to fill out, right? So if I start with -1, then I know it's going to be 1/3, because it's always going to be 1 over my base. When I put in 0, that's always going to be 1. And when I put in 1, I'm always going to get my base exactly. So see how easy those are to graph? Now these circled points over here, I'll draw an arrow to them. You can see that this is all 1, 3, or 1, 2, or as you'll see on this last one. So then on the last one, same thing, we have -1. So we always are going to call that as 1 over 4. 0 will always be 1. And then 1 is always going to be 4. So I don't even have to do any math, really. I just know those are my key points, all based on the base. Based on the base. So depending upon this number, or this number, or this number in my parent function, that's how I'm getting my key points. So if you can think about that, always start with your key points. All right. So that's our base. Our base is considered a common ratio. It's also considered growth or decay. So if we're talking about money growth, maybe our money grows by 5% a year, then we would write that as 105% because we keep the same amount plus 5%, and that's the same as 1.05. And you have some problems like that. Decay is the same way. If I don't know, if something is going to decay, like what decays? I don't know, carbon in science. So it decays at a certain rate. If it decays at 20% per however long, then my decay rate is 20% or 0.2. Okay? And so all these are considered our growth or decay rate, or in other words, our common ratio. All right, so let's look at our asymptote, you guys. Let's look at the asymptote. Very important. In the chat or in your box, either one. Do you guys think we have a horizontal asymptote, a vertical asymptote, or both? So put your guess. Put your guess. What do you guys think? Somebody give me a good guess. Horizontal, vertical, or both? What do you think? What do you think, Bree? Vertical. Ah, yes. Okay. Very good. So I've got both. I've got vertical. I like that you guys are thinking of it on your own. Okay, so what I have so far is I have both, and then I have and then I have a couple verticals. Trevor, are you not guessing? You're saving your guess. All right, so you guys, I can see why you would say vertical, because I think what you guys are looking at is up here, right, along this right side. But remember that by definition, an asymptote means that the line gets really, really close and then never crosses it. So if I look at the red line, it's actually going up and to the right. It's really not angling and getting close to something and then stopping. So if we look at it here, I'll kind of zoom out a little more. I'll keep zooming out here. Zooming out. Zoomed out so much it disappeared. All right, so let's go back to our equation and look at that. So if we have a vertical asymptote, that means then as our x values get bigger, our y values should start approaching some number. But if you picture this, I could plug any big value into x, right? I could put 50 in there and it would be a pretty big value. I could put 100 in there. I could keep putting numbers in there and my y value would grow, 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 grow. But let's think about what would happen if I put negative numbers in there. So if I put negative numbers, so I have right here 2 to the 1. What if I put 2 to the negative 10, let's say? Well, that's going to be 1 over 2 to the 10th power. So 1 over that huge number is pretty small, right? It's getting really close to 0. What if I did 2 over 2 to the negative 100 power, for example? So 2 to the negative 100 power, that would equal 1 over 2 to the 100 power, which is again even smaller and smaller and smaller. Yes, Katie, yes. Oh, I don't know why your computer died, actually. But anyway, so what's happening here is that as I put bigger and bigger negatives in here, my fraction is getting smaller and smaller and smaller, and to the point where it's actually approaching 0. So if we go back to this graph, once again, you guys, notice that all these lines are kind of converging on 0, but even if I keep going to the left, they are not going below 0. So, Katie, your horizontal is correct. That was a trick question, you guys. Very trick question. But now you know. So there is a horizontal asymptote all along here where I'm drawing the red. So the horizontal asymptote is y equals 0. And that is y equals 0. So in all these graphs, we're going to start with y equals 0. And this could potentially shift up, or it could potentially shift down, but we're always going to start with y equals 0. So this brings us to our last question. What does the point 0, 1 represent? Well, that's always going to represent our starting point, right? Our base, our starting point. So, not our base, sorry, our starting point depending upon what our a value is. And our a value in all these is in front of our base, so it looks like this. Y equals a times whatever our base is, we'll call that b, to the x power. All these parent functions have a base of 2, 3, 4, whatever, but there is an a value in front. It's actually 1. So this is 1 times 2 to the x. This is 1 times 3 to the x. And this one is 1 times 4 to the x. You just don't see the 1 because it doesn't matter. But when we start to do transformations, you're going to see that that a value is what's going to end up being here. So we call that our starting point. So for example, in a real life situation, say you deposited $50 into your bank account, then your starting point would be at 0.50. Just like a linear equation, that would be your starting point. And then B would be, by what growth rate does that money grow? So if the money grows at 5% a year, this is going to be 105%, like we talked about. All right, you guys, we're going to actually move on to some transformations. So how are you guys with parent functions? Raise your hand if you have a question. Any kind of question. And we're just doing an overview. So if you if there's something bigger, let me know. All right, you guys are good? All right, how about this, you guys? Because I don't see anybody chatting for a while. How about this? Raise your hand if you are okay. Raise your hand if you're okay. Use the little hand thing at the top and raise your hand if you're okay. Ah, very good. I just have to make sure you guys are there. Okay, so very nice, very nice, very nice, you guys. Excellent, excellent. Okay. And Alicia. Finally, Alicia. She's. All right, good, you guys, good. I just want to make sure. I have to make sure I'm not talking to, zombies or something. All right, so then what we're going to do is we're going to take it to the next level here, and then you guys are going to find key points on your own. So there's no point in finding out about a parent function if you can't transform it, because if we think about contextual problems like the money problem I just told you, that means that we have transformed a parent function to apply to a situation. So exponential functions are always um, using transformations. So let's just review that A in front, that's considered a stretch or shrink in math language, right? The minus h on the end, that is considered a shift left or right. So that's your horizontal shift along your x-axis. And just to remind you guys, okay, good, Unique. I just saw your post. But just to remind you guys, we always shift the opposite way. So if it was, let's just say x plus 2, we would actually shift left. Shift left. 2. So we wouldn't shift right, we would shift left. And then the K on the end is our shift up or down. And that one always goes with the direction that we are shifting. So if we are plus 2 on the end, we would shift up 2. If it's minus 5, we would shift down 5. And then the key thing about K is this is always going to be the value of our asymptote. Asymptote. So if we shift up 5, then our asymptote is going to be y equals 5. If we shift down 2, our asymptote shifts and it will be y equals negative 2. All right, it'll make sense once we start doing a couple too. All right, so let's look at our parent function. So this is the easiest way to graph these. What you're going to do is remember, start with our parent function key points, which is -1, 0, and 1. And some people, when they were doing these, they didn't use all three of these key points. And so it doesn't quite come out very nicely. So always start with these. So remember that the negative means that we take the reciprocal of our base, so that's 1/2. 0 is always 1, and 1 is always 2. Now think about what we did here. Actually, you guys tell me, what is this plus 3 on the end? What kind of transformation is that? So type that in your notepad. What does the x plus 3 do to 2 to the x? What kind of transformation? Okay, good. So which direction though, Miriam? Which direction? So, well, horizontal is left or right though, Miriam, not vertical is up or down. So you're right on the horizontal, but does that mean horizontal left 3 or horizontal right 3? Ah, very good, very good. And so Trevor, you said horizontal right 3. So you guys both got the horizontal, but it's left because remember it always shifts the opposite direction. And the reason why is because x doesn't yet equal 3, right? We have x plus 3. So to figure out which way it shifts on the x-axis, we're finding the intercept. So we set it equal to 0, and we find out that it actually shifts left 3. So, oh, I tried to freeze my video. Is my video not even up anymore, Unique? Maybe that's why. Oh, here, let me see. Oh, Unique, you're at home though, right? So that might be why I'm going in and out on yours. If I'm going in and out on anybody else's, let me know, and then I can freeze the webcam again too. Oh, my voice is skipping. Okay. Hopefully it stops. It's your internet connection. It's too slow, Unique, too slow. All right, you guys, so we know we're going to shift left 3. So that means that we're going to take all our x values and we're going to subtract 3 from them. So we're going to subtract 3 from all our x values. So instead of having a -1, we're going to do -1 minus 3. So -1 minus 3, which is -4. And then instead of 0, we're going to do 0 minus 3, and that's -3. And then 1 minus 3 is -2. So all we did is we shifted all of our x values to the left by 3. And then our y values just stay the same. So we get 1/2, 1, and 2. And that's it. I know, you need a new one, Unique. It's time. It's time. You're going to be a graduate. You need a brand new modem. All right. So you guys, basically this is what I want you to get out of this lesson is be able to come up with your key points using the transformations. Because what are you going to plug in here? You know, if you plug in a 0, then you're going to get 3 or 2 to the third, which is 8, and that doesn't follow our 3 main key points. So start with the parent function. In other words, strip everything off and then apply the transformations. So what I'm going to do for you guys to take it out is you guys are each going to get one in your notepads. You're all so lucky. And then when you're done, and I'm going to do one more with you guys. But when you're done, your ticket out is you're going to, so it's kind of a unique ticket out, you guys. What you're going to do is write an exponential, and we've done this before, but not recently. Write an exponential function with these transformations: a stretch of 20, a shift left of 3, and a shift down of 1. And then I want you to write the equation of the horizontal asymptote for that. And then what I want you to do is write 3 new transformations for the next person. So if somebody else comes in after you, oh, actually that won't work because I have it so that, okay, so skip that part. So just do this, post an exponential function with these transformations. But don't worry about writing 3 new transformations for the next person. So I'll adjust that. The only reason is, oh no, actually I can do that. I just need to open it up so you guys can see everything. So never mind, sorry you guys. I'll go ahead and open it so that you can see everybody's post, and that way you can do this. So write 3 new transformations for the next person, and then make sure you go back and provide feedback on their work after they have posted. All right, so let's look at one of these. Actually, I'm going to do a new one that has a stretch so you guys can see. Okay, so actually, no, we won't. Oh, Alicia is back. Maybe I'll just do one of the ones you guys aren't doing. Okay, so number 6, I'll do that one because nobody's in 6, and that's kind of a hard one. So if we look at 6, what we do is we start with our parent function, and you guys can always identify the parent function because it's this base. So our parent function is y equals 2 to the x. So I would write that and come up with my key points because that's going to be easy for you guys to do. So we know it's -1, 0, 1, and then it's 1/2, 1, 2, because we've been doing that. All right, now we're going to transform. So if I identify my transformations, I know I'm going to shift right 1. So that means I'm going to add 1 to all my x values because I'm shifting right and left, which is an x. And then I'm going to add 5 to all my y values. So I'm going to do y plus 5, like this. So -1 plus 1 equals 0. 0 plus 1 equals 1, and 1 plus 1 equals 2. Oh, Trevor, oh, you have to go? Oh, that is a bummer. Trevor, I think you just don't want to do this. You're leaving us. But no, if you need to go, that's totally fine. And then y plus 5, so on this one we're going to take 1/2 plus 5, which is just 5.5. And then we're going to take, Alicia, why do you keep going in and out of my room? 1 plus 5, which is 6, and 2 plus 5, which is 7. So those are my key points. And then as far as my asymptote, I'll know that I have a new asymptote if I have anything out here. So whatever that is, y equals 5 is my new asymptote. Now you guys, just to show you graphically, let's look at what this looks like. So -1 and +5. -1, oops, wrong place. -1 and +5. So what I'm going to do is I'm going to graph it. I'm going to show you. So y equals 2 x -1 and then +5. So here's my graph. And I'm going to hide the other ones so we don't have all that distraction. So you guys notice that on this graph, and I'll move this back over so you can see. Notice that on this graph now, the bottom of it is raised up to 5, right? So I'm shifted up here, right here where my cursor is, if you guys can see on your screen. I don't know if you can. Right in here is the horizontal asymptote where y equals 5. And actually I could put in an equation for that, y equals 5, and then you can see that black line right there. That is our horizontal asymptote. Is that coming up on you guys' screen? Hopefully. Oh, there it goes. Okay, so anytime you have a plus 5 on the end or plus something like this or a minus something, that is going to be your new horizontal asymptote. Sorry, guys. Graphing is kind of complicated. This is true. All right, so what I want you guys to do then, and you can ask me questions as you go, is from your notepads, all you have to do is find the key points and tell me what the asymptote is. So just tell me what the key points are and the asymptote. That's all you have to do. And once you finish that, then go ahead and make your post in Schoology. Let's see. So you have -1, 0, and 1. So your key points are 1/2, 1, and 2. And then when you add, so Miriam, what happens when you add? Oh no, you're subtracting. Sorry. Oh, so you subtracted. Never mind. That looks good. So you subtracted 3. So you're going to do x minus 3. See how you did. And y stays the same. So you got -4, -3, and -2. Perfect. And your y's are staying the same. And okay, so Miriam, here's the last question then. What is the equation of your horizontal asymptote? If you can tell me that, you are done.